All right, good afternoon, everyone. So we're going to continue our discussion of PCA today. And just to summarize what we did last time, the idea behind PCA is we want to reduce the dimensionality of our features because we want them to take up less space, or we want it to do some subsequent task with less computation. And so the idea behind PCA is to find a subspace of our higher dimensional feature space that is basically the best match to the data. We choose the dimension of the subspace, but then PCA figures out how to orient that subspace so that it's the closest match to the original features in the sense of RSS. So here's some pictures where the original features are three-dimensional. And in the left plot here, we choose our subspace dimension as 2. And so PCA finds this plane here. And this is the plane. It's oriented so that the sum of these error terms, sum of squared errors, is minimum. And on the right, if we instead chose to approximate the data with a one-dimensional subspace, then PCA is going to find the line that is the best approximation to our data, which means that the sum of squares distances from the points to that approximation is minimized. So that's the idea. There's actually a typo I just noticed on this page. So, so PCA is only an approximation. So this should be approximately equal to, not exactly equal to. So the way that it works is we approximate the original features by a fixed matrix times some features that have a smaller dimension. So this is like something like this. So here's our original dimension, which is larger than the approximated dimension here. We called this D, we're calling this R. And the way that we construct this matrix, VR, it's the matrix built from the R principal eigenvectors of the sample covariance matrix. The sample covariance matrix, we've seen this before, we're calling it Q here. It is the average outer product of all of our data samples. And we can also write it in terms of the data matrix like this. And the way we compute these these small dimensional approximations are we multiply VR transpose times the original features xi to get us z hat I. So once we do this, the idea would be you throw your original data away. Now you have a data set that it's compressed and that the features are smaller dimensional, and you work with that. Now, not surprisingly, you have lost information, so you don't expect that this works as well as before. It's a form of lossy compression, so you expect that there will be some performance decrease, but that's the trade-off. You have to choose this R so that you have good enough behavior, but it's enough compression, the data dimension is small enough that it's useful to you. So we'll see some examples today with faces and some other things. All right, any questions on the overall idea behind PCA? Okay, so what we're going to do next is we're going to focus on how exactly do we compute this matrix. We know we have to do some sort of eigendecomposition, but there's something that's a little bit faster, a tool from linear algebra called the singular value decomposition, the SVD. How many of you guys have heard of the SVD? Okay, SVD, super, super useful. It's my favorite of all decompositions in linear algebra. It basically, one of the things about it is that it works for any matrix. So a lot of decompositions in linear algebra only apply to matrices that are maybe square or full rank or something like this. SVD, you can apply it to any matrix. It can be tall, wide, square. It can be not full rank, whatever. But what the SVD does is it decomposes it into a product of matrices that are each very interpretable. So here, U and V are orthogonal matrices, meaning all of the rows are orthogonal to each other. all of the columns are orthogonal to each other, all the rows are unit norm, all the columns are unit norm. And then S is a diagonal matrix. So overall, when you look at this, the interpretation that I like to use is that multiplication of a vector by X can be thought of for any matrix X as a three-step process: a rotation, a scaling, and another rotation. Okay, so multiplication by X, any sort of linear transformation, any linear system you can describe with a matrix multiplication for finite dimensional linear systems. And it basically then says that any linear system can be written as rotation, scaling, and rotation. So that's a very useful interpretation. And this helps for a lot of proofs when you want to try to prove or understand what's happening with matrices. Often you plug in the SVD, you do a bunch of simplifications, and all of a sudden the answer is kind of obvious. So that's what's really great about the SVD. So there's really actually two common versions of the SVD. The first one we're talking about, which is the standard SVD, let's see. Maybe I'll just change colors here. Okay, so the standard SVD, we have square matrices, U and V, more than square, they're orthogonal. And then X and S have the same dimensions. Okay, so just to give you an example, let's say that X is tall. Then you're decomposing it into a square matrix of the left dimension times a diagonal matrix of the same size as X times another square matrix that has the column dimension. That's how we're decoupling it. Another thing about this diagonal matrix is that the elements along the diagonal, these guys here, they are ordered from big to small. It is possible to have, in some cases, you have several with the same value, but generally speaking, big to small. I'm trying to think if there's anything else. I think those are the main points behind the standard SVD. Now, when you look at standard SVD, you might notice that there is some, you could say, redundancy. So notice that all of this stuff down here, this is all zeros. So if you think about this matrix multiplication here, all these zeros over here will multiply all of those terms in a way that these terms are meaningless because they will be zeroed out by these. So you could say, well, why should we go through all the computation of figuring out those terms? So in practice, often you want to use a more computationally efficient version of the SVD that simply does not compute any of these things that will be multiplied by zeros. Okay. And there's even another version of this that I'll draw now. So another version of this would be, let me erase these. Imagine that I have a few non-zeros here, and then all of these are zeros. So in that case, you can see that actually all of these are zeros. They will multiply all of these, essentially making them meaningless. And this stuff here will multiply all of these, making those also meaningless. So really, the only ones you care about, if there's, let's say, R of those, you only care about the first R columns here and the first R rows here. And the economy SVD computes only that stuff. And so, so it looks like this. Now in this case, for that same picture above, we would have, I'll put maybe a dashed line here to show that we're only computing those columns. And then we're going to have a small matrix here, which is only computing the non-zero portion. And then we have a wide matrix here, which is only computing those rows. Okay, so in this case, what you find is that this matrix is square and invertible, meaning no zeros along the diagonal. It's diagonal and no zeros on the diagonal. These other matrices here, because they're built from these columns, we know that all the columns here are unit norm and they're orthogonal to each other. Same thing with these rows. These guys are all unit norm orthogonal to each other, but it's missing all of these other columns, and this guy is missing all of these other rows. Okay, so that's the difference between these two. So you could say standard SVD is square U and V, economy SVD is square S. In this case, these are square orthogonal matrices here, so you have these nice identities. U times U transpose is identity, but also U transpose times U is identity. In this case, UR is tall, and so this multiplication is like a wide times a tall. Sorry about that. Okay, so you can see this is going to be a wide matrix times a tall matrix equals an identity matrix. But if you think about the other multiplication, or let's say this multiplication, the outer product, there's no way that that could be the identity. So that would be like UR transpose. So in this case, we can say both of these are true, but in this case, only one of them is going to be true in general. Okay. And as I said, these are all strictly positive. Okay, so those are the two forms of the SVD. The second one is computationally, there's less things to compute. That makes a difference, especially when these matrices are large. The first one is often more convenient for theoretical analysis, but sometimes the second one is also convenient because this S is invertible. Okay, so that's the SVD. And then what we'll do next is we'll show how we can use the SVD to compute the quantities we need for PCA. Are there any questions about SVD? Okay, so again, very, very useful transformation. Okay, so thinking back to PCA, remember that we need to compute, well, the way that we described it before, we have this sample covariance matrix, and we said that if you have the sample covariance matrix, you could then do an eigendecomposition of it. And in this case, when you look at this eigendecomposition, actually it looks very similar to the SVD that we had on the previous page. And we can compare them directly. So if we take this expression, the definition, and we plug in for X, U, S, V transpose, and then for X transpose, we have V, S transpose, U transpose. Plug those in, we get this, and immediately we see we have this U transpose U. Because U is orthogonal, we know this is identity, and so we can basically remove that identity. We can also bring this into the center, and we have something of this form. And now you can notice that essentially these two are the same up to a definition, to a naming of the diagonal matrix, because we remember that in the eigendecomposition, we had orthogonality, so V is an orthogonal matrix, but we also know that down here in our standard SVD, V is an orthogonal matrix. Okay, so actually the V for SVD is actually exactly the same as the V for the eigendecomposition. And in the middle, we have a matrix of real numbers, non-negative numbers here, and we also know that's going to be the same here. This is also going to be a diagonal matrix with non-negative numbers. So now we can see exactly the connection between the eigenvalues and the singular values. Turns out that the ith singular value squared over n is the ith eigenvalue. So that's it. The advantage of working with, a possible advantage of working with the SVD rather than this Q matrix is that when X is really big, even computing the Q matrix can take a lot of time. With the SVD, you never actually compute the Q matrix. You work directly with the X matrix. You do the SVD on that, and then that gives you can actually throw away U because it doesn't matter. You basically keep V transpose and you keep the singular values in S. Okay, so just in doing that, you can find that in many cases there's a big speed up because you don't actually need to compute Q. Okay, so that's essentially what we're going to do. And furthermore, remember we have like the standard SVD and we have the economy SVD. We can actually use the economy SVD as well. The advantage in the economy SVD is that instead of having computing these big square matrices, if the rank of our data set is such that we have some zeros in here, then we can settle for tall matrices. We don't have to compute all the entries in the square V. So that's essentially what we're going to do. Compute PCA with the economy SVD. This is less computational complexity than the standard SVD. And remember that for PCA, we actually don't need even all of these eigenvalues, right? Because we're only going to keep the top R of them. R, capital R, that's our design choice. So what we're going to do, we're going to compute this economy SVD, and then we'll keep only the first columns of this tall V matrix. We'll call that V sub capital R. Once we have that, we can apply that to our data samples, our original features, to get our compressed features, ZI. So these guys will have smaller dimension. They are going to be R-dimensional, whereas the XIs were D-dimensional. So that's how we do our compression. Okay. All right, so any questions on how we're approaching this? Okay, so that's basically, that's how we do PCA in practice using this economy SVD. And the next question is, let's think forward and say, usually we're doing PCA because we're going to be doing something later with the data. And one of the things we saw is that in many cases we want to have features that are standardized, meaning zero mean and unit variance. So these ZIs, these are our new features. So you might ask, well, what does it take to make them standardized? So let's take a close look at that. Okay. We should standardize our new features ZI. So in particular, we know that standardization means the sample mean, the mean of all the Z's across the I should be the zero vector, and that when we look at the jth component of ZI, if we average the squared jth component of ZI over all the I's, that should be 1. That's our, together this is zero mean unit variance. Okay, so let's rewrite this guy in terms of the sample covariance matrix. So the first step is to realize that, let me try to visualize this. So let's say I have ZI times ZI transpose. So that's going to be a whole matrix, right? But what if I just look at the diagonal terms of that matrix? So if I look at the diagonal terms, that means that if I'm looking at the jth diagonal term, I'm going to be looking at the jth entry of that vector and the jth entry of this vector on the right. And that is exactly, when you look at that, now you have this quantity times the same quantity, so basically that gives you the squaring. And so essentially, this diagonal of this average outer product gives you all these squared terms, j going from 1 to n. Or actually, we care about this mainly from, 1 to r. So this is just, here I'm saying that each value alone should give 1, and here we're saying that together they should give the 1's vector. Okay, so this is just a way of writing this directly in terms of the QZ matrix. This is just the sample covariance matrix for our Z data. The reason we're doing this is that we can then work more easily with this sample covariance matrix. Okay, so let's see what this implies. So taking the first condition, Z hat, okay, by definition we know that Zi is VR transpose Xi, so we plug that in. We can move this averaging through the VR, apply it to the Xi. And then remember, here we just have the sample mean of the Xi features. And remember that we already said from the beginning, these are centered, meaning that sample mean is 0. So if that sample mean is 0, then VR transpose times 0 is 0. So actually, Z's are already centered. We don't have to worry about that. Okay, great. So let's move on to take a look at this sample covariance matrix. So as we said, this is like the average outer product, Zi times Zi transpose. And again, we're going to substitute for Zi, substitute in this. And so that gives us VR transpose Xi and then Xi transpose VR. And here you can recognize this. This is the sample covariance matrix of X, which we called Q. We know that we have this singular value decomposition for Q. We can plug that in. That's going to be 1 over n times this stuff. And now we can simplify things a lot. So if you remember VR, the VR matrix contains the first R columns of V, and then this VR matrix contains the first capital R columns of V. Also, all those columns are independent of each other, or they're, orthogonal to each other. So when you do this, this inner product, basically you find that the first R entries of that matrix, capital R entries of that matrix, give you identity, because essentially that's like V capital R transpose times VR, that would be identity R. And then there's another part here where you're looking at the columns in here that are not in there, and so because of that orthogonality, you get zeros. And so finally, all this does is it extracts the first capital R entries from this, and you're doing that from both sides, and so you finally get this diagonal matrix that has only capital R entries. Okay, so again, our objective was to make the diagonal elements of QZ equal to 1, all of them. And now we see that that QZ is already a diagonal matrix. So all we're asking for is that each of these values equals 1. That's very easy to do. We just have to take this and multiply it by, let's say we look at the Zi vector, we scale the terms this way. So this is just the square root of the inverse of that. And essentially, we're scaling Zi, so we're scaling this, and we're scaling this, and together, they're going to give us a squared effect, and it's going to turn this diagonal into an identity matrix. So to summarize, Z hat is already centered, and ZI does not satisfy this directly, but if we scale things, we scale the elements of ZI in a particular way, we have these new standardized features that we're calling Z tilde I. So these guys are zero mean and unit variance for all the entries. So this is what we'd want to use if we first did PCA and then we did some sort of regression or classification method where we would like to have standardized features. Okay. We'll do an example of this later in the lecture. Okay, so basically we learned how to do PCA using the SVD, and now we also learned if we want to standardize the coefficients that PCA gives us, that's also relatively easy to do as well. Okay, any questions on this? All right, so let's move on to working with the data. So on Monday, we talked about this face data set. Let me just remind you, we have an X matrix. So each one of the rows in the X matrix is a face image that's been rasterized, it's been turned into a row vector. And we have 1,288 faces, and the dimension D of each face is 1,850 pixels in every face image. Okay, so that's our data. So we want to first, we compute the mean of each one of the columns, store that in the X mean vector, and then we subtract that from X to get the, what do we call this? The zero mean version, standard version. Okay, and we can do that subtraction because this is a row vector and this is a matrix. We use the PyTorch broadcasting to temporarily turn this into a matrix so that we can do the subtraction. Okay, so now we have the center data. We use NumPy linalg SVD. We say full matrices equals false to get the economy SVD. We plug this in. And different from MATLAB, MATLAB would return USV. NumPy returns USV transpose. So that's why I named this variable VT. And to verify that this is V transpose, we'll plot the shape of it, and we see that V transpose is a wide matrix. And we know that V must be tall, and so that confirms that, yes, that is the transposed V matrix. And this has the dimensions that we might expect. This is just V, essentially, in this application has the same dimensions of X, the data matrix. Okay, so this is the dictionary matrix that we use for PCA. We know that the performance of PCA, we talked about this proportion of variance. Basically, for proportion of variance, as a function of how many components R we use, it looks like this. So this D dimension is fixed. It's from the original data, and R is our choice. So in the demo, we construct a plot of this quantity versus R. So as we go along the horizontal axis, we compute this for increasing values of R. So if I want to get this as a vector for increasing values of R, you'd call that a cumulative sum. You're summing these guys starting from 1 up to R, and first time you just get the first element, and then you sum the first 2, and then you sum the first 3, and you sum the first 4, and so on. That's the cumulative sum. And then we're going to just normalize that. So let's look at the code. Okay, so this is, okay, first we create the lambda vector. Remember, the lambda vector is just the singular value s squared divided by the number of samples. So now this is a vector of lambda coefficients. To get this proportion of variance, we do numpy cum sum lambda on the top over numpy sum lambda on the bottom. And this gives us a vector, and we can plot that vector versus just plot that vector versus its index, which is the number of principal components. And we see that the proportion of variance climbs up towards 1. Remember, if it's exactly 1, that means we have a perfect approximation. So you can see it gets pretty close to 1 already at 400 samples. It's almost 1. And it's hard to see visually. It looks like it's exactly 1. It's just a little bit below 1 all the way until this last point here, and then it's exactly 1. Okay, but what this plot here tells us is it tells us essentially how to choose R, the number of principal components. You can see that there's really no point in choosing R more than 400 because we're so close to perfect at that point. In practice, you might actually want to choose R somewhere down here. You accept that there might be a little bit of error, but maybe, if you choose R at 100, maybe this is good enough, and 100 is, a lot less than 400, which is, again, a lot less than 1850, which is the full feature dimension. Okay, so this is how we can justify choosing R of maybe 400 or 100 or something like that. Okay, so let's look at some pictures. So now what we'll do is we'll try to reconstruct. This is the full face. We're going to try to reconstruct from or approximate from the eigendecomposition. And here you can see plotted in the top, this is the rank of the approximation. So this is PCA with 1 component, 3 components, 10, 30, and so on. And you can see that as we use more and more components in PCA, the approximation gets better and better. Here we are at 300. We saw on the previous page that 400 was almost perfect. 300 is also pretty good. And visually, yes, things are quite good at 300. Same thing for this image here. It's hard to see many differences visually at 300. 100 is definitely, you can see you've lost some details, but maybe if your objective was to classify whose face this is, maybe you don't need 300 to do that. Maybe this is good enough to figure out whose face that is, right? So we really have to think about what is the downstream task. That, in addition to, this is sort of a generic metric, but that in combination with what's the downstream task can give you an idea of how to choose R. What's also really interesting is, sorry, this should say principal, wrong version. Okay, so here's the mean image. Remember that the very first step is we have to subtract the mean from the data. So that's sort of interesting. If you just average all the faces in the database, you get this. And these are the principal components. These are the V's. So this is like V1, V2, V3, and so on. What we know about these V's is that they're ranked in order of importance, right? Like if I want to do the best third order or rank 3 approximation of my faces, what it says is I use the mean and I use linear combinations of these 3 vectors, if you will. And that is the best way to construct the faces in the data set from the RSS perspective. If instead you tell me I want to rank 4 approximation, then I would, in addition to those, I would add on this one, and so on. Another thing we know about these is that they are orthogonal to each other. So if you looked at the inner product between this and this, you would find that it's 0. If you look at the inner product between this and this, that's 0. The inner product between this and this is 0. So they're all mutually orthogonal. And remember that with images or matrices, the inner product would be computed by pointwise multiplying this times this and then summing up all the outputs. That's the inner product for a matrix. Okay, so that's sort of interesting. Something to keep in mind is that this face, I don't remember exactly how it's scaled. The pixels are either scaled from 0 to 1 or maybe from 0 to 255. That's a common way to scale images because it's an 8-bit representation. But the point is all these pixels are non-negative, and same with the mean. Whereas here, these guys will have negative entries. There will be negative and positive and maybe 0 pixels in all of these. So in that sense, they're not really valid images because we wouldn't know like what brightness is negative. Black is 0, so there is no such thing as blacker than black. But it's just one of the special things about how PCA breaks apart a data set into components. In the next unit, we'll see another approach, which is a different way of breaking things apart, called non-negative matrix factorization, that breaks things apart into only positive factors. And we'll see that it has a very different behavior than PCA. In some applications, it works a lot better. But it's just a note that this is one way to kind of unpack a data set or break it into components. It's not the only way to do so. All right, so I think these are kind of fun to look at. These things are known as eigenfaces, all of these things. Okay, any questions on this? So here the objective, you could say, was to get a good-looking face, a face that is a good approximation of the true uncompressed face. We could also shift our goal to face recognition, which is now a classification problem. So here, of course, we need labels, but this data set does have labels. There's, this is George Bush shown here. There's a few other people in this database. So let's see how we can use PCA for face recognition. So the very first step would be to take our original data, split it into test and train partitions, and then we want to center the training data. So we compute the mean of the training data, subtract that from the training data. We'll, of course, have to subtract that same mean from our test data later. And then we get ready to do our PCA by computing the economy SVD of the training data, because that's U, S, V transpose. And so our eigenfaces, that's just this dictionary matrix, the V transpose from the training data. And here I'm going to choose 100 as the number, as the rank of the approximation. So I'm just going to choose basically the first 100 rows of V transpose. That's like the first 100 columns of V. And then to make my compressed features, I have to basically do this. This is basically a row-wise picture of what's happening. Like this could be the entire X matrix. This would be the entire Z matrix if you stack those guys. So that's what's happening over here. You have the entire X transpose matrix times your V, which is the eigenfaces transpose. And then here you have the entire Z matrix. So in this step, we have done our PCA. So now we have our compressed features all organized into a matrix. That matrix has 100 columns and 1,288 rows. Okay, and the last step is to standardize the coefficients, because that might be important if we do classification where we are using some sort of regularization term. And we know that that's pretty straightforward. You just have to scale each row, and we know you scale it by the singular values. That's STR. So here's the singular values, and we're again using Python broadcasting to do this division, and multiply it by the square root of the number of samples. So now we have our zero mean unit variance features, and we can move on to doing classification. So we're going to choose to do classification using a support vector machine. We're going to use the radial basis function kernel. We have to choose the regularization C and the kernel width gamma. Those are super important to get the SVM to work at its best. So we're going to make a grid of usually with C, you want a logarithmically spaced grid of C values, a logarithmically spaced grid of lambda values. So we'll search over all those combinations. We can do that using grid search CV. The estimator, as you can see, here's our SVC with our RBF kernel. And we're using 5-fold cross-validation. And once we're done with the grid search CV, the best estimator is stored inside this object, and we can then use that fit that estimator to our full data. So here we're doing things with cross-validation. Eventually, you want to use the full data set for training. So that's what's happening in this step. And we can also print out the best estimator if we want to see what were the gamma values and the C value. Where's the C value? Oh, here it is. We want to see what parameters were chosen. And also, this tells us the best cross-validation accuracy, which turns out to be 85% accurate in recognizing these faces. Now, you might say, I really care also about how it works on the test data fold. This is all just cross-validation on the training. So we can go through and do the usual things. So first, we take the test data. We have to subtract not the test data mean, but the training data mean from it to get our centered test data. Then we compress. We use exactly the same dictionary. We get our compressed test data, our features, and then we do, once again, the scaling using the same parameter found on the training data. Finally, we use this estimator that we found here. We do the prediction to get our class labels. We value our accuracy, and we find out it's 83%. And that's pretty close to 85, so that's it's good. We expect pretty good agreement between these two, but not perfect. And so this is just an example of how you could use this. Now, you might say, well, how does this compare to not doing any PCA approximation? That's a good question, but that would take a long time, because when you do these grid searches, as you probably know, with the SVC, it can take a long time, right? And with our original data, the features are just that much bigger. Here we're using 100 dimensions, so it's small enough that we can actually tractably do this, but if we were using, what was it, like 1580, maybe that would have been too difficult. Okay, so I don't know exactly how well it performs on the full coefficients, but seems to perform decently well on the compressed PCA features. Okay, so are there any questions on anything so far? So we've seen how it works with visual quality. We've seen how it works with classification. So the last thing to talk about is here is just to remember that there are limitations to PCA. So first of all, there's many, many different ways that you could attempt to reduce dimensionality, to compress your features. PCA is special in that it's linear and it minimizes RSS. Those two things together make it very computationally or analytically tractable, and they allowed us to derive a closed form solution. If you tried to do something nonlinear or you tried to be more clever than use RSS, it's much more complicated and you probably cannot derive a closed form expression. Maybe you can train a network or do something like that, but you can't derive something in closed form. So that's the nice thing about PCA. It's very straightforward, it's very simple, but it's not always the right thing to use. So let me show you one nice example. PCA cared about minimizing RSS, but minimizing RSS is not necessarily what you want to do for classification. So let's look at this example. So we have a data set, binary data set. So here, this is basically just two-dimensional data set. We have feature 1, feature 2. So you can see for all these samples, we have class 1. All these samples, we have class 2. The data is linearly separable. So if I did the classification in the full feature space, it would work very well, right? Could apply a linear classifier and we would get perfect training accuracy. But now our goal is to compress the data. So compression means going down to one dimension. So if you look at this data and you say, how would PCA compress the data? PCA looks for the plane that has the smallest difference of these projection errors. Right? And if you think about all the different ways to put a plane here, here you'd have some pretty large projection errors. If you put the plane here, that's going to be the best. Relatively small projection errors, the smallest you could do. So PCA would put the plane here and then to project everything onto that plane. So this is what it would look like after you're done with PCA. You'd have those data samples. And now you can see it's impossible to tell class 2 from class 1, right? They're all smushed together on that line. If you knew you were doing classification in advance and you said, I have to choose one direction onto which to compress my data, you would actually, for this data set, you'd want to do this. So all these guys would be compressed to here, and all these guys would be compressed to here. And in one dimension, it's still linearly separable. It would work perfectly. But PCA is not going to do that. PCA is going to work the other way. So this is just to show you how PCA can fail when the final task is classification. And that's because PCA is designed to minimize RSS, and minimizing RSS is not necessarily what you want to do for classification. So it turns out that there is a classical technique called linear discriminant analysis. It's a classical form of linear dimensionality reduction. And there, the whole goal is to discriminate between two classes. And LDA would actually choose that line, and it would give you a nice one-dimensional classification problem. So because we don't have much more time in the semester, I'm not going to teach you any more about LDA. LDA is not something that I really see people widely using today, so I don't think you're missing a lot if you don't know about it. But of course, if you want to learn about it, you can click on the green text here and you can learn more. So this is more just a warning that PCA is in general, it's something that's going to save on space and processing time, but it's going to hurt in performance. And in some cases, it can be disastrous in terms of performance. All right. Okay, any questions on this? All right, so there's one more application that's important that people use PCA for in some cases, which is data visualization. And the idea here is that if you choose an R of 1 or 2, you can very easily visualize your data set. So you squeeze everything down to a plane. And so here's just one simple example where we start in 3 dimensions. So we have 3-dimensional data. When we look at this, it's kind of hard to see what's going on. In this case, the data is labeled, and it's labeled with different colors. It's not really important for PCA, as we know. PCA doesn't use or need labels. In any case, if you applied PCA here and you squeezed the data down to 2 dimensions and plotted it, you would get this plot, and now you can see things are very nicely clustered together. So again, you can ignore these colors if you want. Even if they weren't colored, you could see that the data is pretty well clustered into 4 different clusters. We'll talk more about clustering in the next unit, but visually you can see that the data is organized, right? Clearly organized. And that's easy to see in 2 dimensions. It's harder to see in 3 dimensions. And if it was in 4 or higher dimensions, we humans can't really visualize in 4 or higher dimensions. So that's why people care about projecting down to 2 dimensions or in some cases 3 to try to visualize data. So PCA is definitely one way of doing that. So let's look at what happens if we apply PCA to MNIST. MNIST is a nice data set. We've seen it, we understand it. So if you remember in MNIST, that's the one where there's 10 different digits, handwritten digits, 0 through 9. And what we're showing here is how, okay, so we're using PCA to compress the MNIST, I think it was 384, if I remember right, 384 dimensional little pictures. And now we're squeezing everything down to 2 dimensions. And we're labeling the samples according to the digits. So these are the 9s, these are the 8s, and so on. down to these are the zeros. So the first thing you notice is that there is some structure. There is some, these guys are grouped together, these guys are grouped together, and so on. But it's not clearly separated. So PCA is, maybe we would hope that PCA would just cluster things, it would clearly separate the zeros and the ones and so on. It's not doing that. But it is sort of interesting to look at. And another interesting thing is here we're showing this is the first principal component, and this is the second one. And in these pictures, we're using gray to represent 0, blue to represent positive, and red to represent negative. And so if you just imagine going sort of along this line, what you're doing is you're just, you're multiplying this by a sign. So if when you're positive, basically the blue is positive, this is negative, and when you go in this direction, then the blue becomes negative and this becomes positive. And what we are seeing here, is like a kind of like a correlation between the principal component and the sample, and you can see that over here, it makes sense that the true zeros are very positively correlated with this outer blue ring, and that's kind of why these blue zeros are on this side of this feature space. And on this side of the feature space, these ones are positively correlated with this thing here. Okay, so that kind of makes sense. So that's sort of separating the zeros from the ones. But then, you have all these other digits, and you have to, to get a better view of how to separate them, you have to look at the second principal component. And here you can see how it has a positive here and a negative here. And by different combinations of these, you can construct an approximation to those other digits. So it's just kind of nice to see how PCA is kind of unpacking MNIST, not perfectly, but it's definitely learning things that have meaning and doing some sort of separation, although not a perfect separation. Okay, any questions on this? Okay. So obviously this is not working very well. But again, PCA is very simple. So maybe there's other approaches that are better. The answer is yes. So we would in general want to use a nonlinear dimensionality reduction approach. So PCA is linear. Nonlinear is going to be much more powerful. And there are many classical techniques that have been developed for this. Kernel PCA, isomap, local linear embedding, and so on. They don't work that well, but there's some more modern methods. Some of the most well-known are TSNE, UMAP, PACMAP, and here is how they work on MNIST. And you can see that TSNE and UMAP actually do quite a good job of separating all the classes within MNIST. Now, the thing I want to emphasize is that TSNE and UMAP do not know the labels. Okay, all they get are the MNIST features. They have no idea what the labels are. And then you're just asking both of these techniques, can you just find the best two-dimensional approximation of those features? And it's kind of remarkable that when you do so, they naturally organize things into clusters that actually agree with the labels that they have never seen. So it's kind of amazing, right? This is unsupervised, in contrast from supervised classification, like what we talked about in earlier chapters when we talked about classification. We were building methods that knew the features and the matching label, and yes, they were able to do a decent job of classifying MNIST. But here we have techniques that have never seen any labels, and just from the features alone, they can recognize that all these are similar and different from the others, all these are similar and different from the others, and so on and so on. Actually, UMAP is does an even better job than TSNE. So that's kind of that's what's significant about these methods. And the way that you can use them is sort of a proof of concept. Let's say that someone gives you a data set, and it's data you've never seen before. You just sort of wonder, like, is there some way of separating, of classifying this data, or even separating it into different, pieces? You can just give it to UMAP or TSNE. You have a few parameters to adjust, but you can tweak them. And you can get an indication of, yeah, actually, if this is what you get from UMAP, then yes, there is going to be a classifier out there, especially like a supervised classifier, that's going to do a good job of classifying that data. Because UMAP did a good job of clustering it without even knowing anything about the labels. So if I also tell it the labels, yeah, that definitely should work. On the other hand, if you apply UMAP or TSNE to a data set and it's just completely all mixed together, you might be more pessimistic about whether it's even possible to classify or to separate it. You might be like, nah, this is too hard. Okay, so that's typically how these are used. They're sort of like early data explorations before you approach the problem with other techniques. Okay, so that's all we have for this unit. And then there's just one final unit in the class, which we'll talk about starting Friday, which is on clustering, basically ways that try to take a data set and separate it into clusters like this. And we'll talk about an application of language text processing. So we'll also see some new data sets and new ways of thinking about data. So that's it for today. See you guys on Friday.